Lukas Muller talking to us about higher categorical structures of topological defects in quantum field theories. So please, Lukas, go ahead.
Yeah, thanks for the invitation. Thanks for having me. I'm sorry for not being able to be there in person. It was unfortunately not possible to some, related to some visa issues with the Canadian government. Anyway, so my talk is about trying to explain a bit to you what type of structures topological defects in quantum field theories form. And feel free to ask questions at any time. Especially not being in the room, it's hard to really feel how the audience is getting along. So if you have any concerns, if something is unclear or you want to see more details on something, just feel free to ask questions. As I said, at any time. So fine, let's get started. I mean, topological defects really have become a topic of immense interest in physics and also mathematics more recently, and I'm just somehow trying to give you my perspective on a small aspect of the field. I will ignore many things, but for today, the main focus is the higher categorical structure. And since this is a meeting on defects, I think I don't really need to spend much time introducing them. Just briefly recall that somehow we call defects topological when they satisfy the property that if we compute a quantity such as the path integral or partition functions or observables, the answers we get don't really change if we deform our defects in a continuous way. So here I have some line defect, and the answer I get for computing a partition function should agree even after deforming them. And then there's this belief in physics, which also has been established in various mathematical contexts, that if I look at the collection of all topological defects and quantum field theories of some space-time dimension n, then this structure should assemble into what's known as a higher category, which encodes somehow all the algebraic aspects of the theory of topological defects. So let me briefly explain how, from a physical perspective, and also a bit from a mathematical perspective, one thinks about it. So what one looks at are usually local configurations of defects one has in Rn. So n is always the dimension of space-time. For me here, this would be 3 dimensions. And then for simplicity, I have 2 quantum field theories, which I denote by A and B. And now if I have a surface defect between them, like this pink object F here, I think of this as being a relation which goes from A to B. So in the world of categories, I would write 2 objects A and B, and then a morphism F, which relates them. I can have another surface defect between them, which I call G, which is also a morphism from A to B. And now there are relations between surface defects in 3 dimensions, which can be implemented by topological lines. So I could have 2 topological lines here drawn in red and blue, and then they would give me 2 different ways of relating the morphism F and the morphism G. And then finally in dimension 3, I can also have point defects sitting on lines, which somehow relate these 2 morphisms between the 1 morphisms. So roughly speaking, there's some 3-layered structure which encodes relations between defects and so on, which are all implemented by defects. And now you might generally complain if I look at the picture like this, how tells me how to read this picture? Because I've drawn it somewhat arbitrary. I could have drawn, so for example, there would be I could have drawn it differently, but also maybe you would read it left to right, or right to left, or maybe you want to read it top to bottom, bottom to top. So there's somehow a lot of choices I need to make to take such a picture and really turn it into a morphism in some higher category. And throughout the talk, one important thing is that will be that we should keep track of these structures. So roughly, I will somehow need to give some redirection in R3, which tell me in which directions I read morphisms. So it says like here, this arrow explains that I read 1 morphism in this direction. Then I read 2 morphisms in this direction, and 3 morphisms in this direction. And I indicate this by drawing these things, which are sometimes called framings. And then the two morphism also has its own framing, telling me in which direction I read it and so on. This somehow additional structure we need to put on our defects if we want them to form a category. And now you might wonder or complain that in many physical settings, we don't really have this extra structure present. And my talk roughly will be about what not having this way of picking a preferred direction, what extra structure does this give on these categories. I should also say categories somehow do not only consist of this structure, but in addition, some type of composition structure. So if I have two topological, let's say, surface defects, which I denote F and F prime, again, with the convention that I read things in this direction, then I can bring them close together. And for practical purposes, they look like a new surface defect, which I define as the composition of F and F prime. So this fusion of defects really corresponds to the structure of composition. So roughly, so the slogan is that this higher category D really encodes all the topological defects I have and their fusion and how they interact. And yeah, as I said, I think somehow what I want to discuss is what type of structures these categories have. And I will focus on a specific aspect of it. But let me first highlight some open questions or something which I think is somehow not fully rigorously established within mathematics, namely how do I construct these categories D concretely, or how do I construct them? And it's a bit hard because somehow we want to construct objects related to quantum field theories. However, quantum field theories often are hard to define themselves. So it's hard to somehow start with a quantum field theory and get a mathematically rigorous constructions of building these categories of defects. However, there are various approaches to axiomatization, and one can try to implement these strategies in these. And this has been done a while ago in a framework known as functorial quantum field theories in dimension 2, where these bi-categories have been constructed in the setting by Davidov, Kohn, and Wonkel. And then there's a 3D version for topological field theories, extending their arguments by Cargill, Moisburger, and Schaumann from a few years ago in a different axiomatic framework to fully extend the topological quantum field theories. Following Lurie's work on the stratified cobordinate hypothesis, these categories of defects are just built in by definition. So one needs to start with a higher category to formulate topological field theories. And then the morphisms in this category will be also correspond to topological defects. And I want to highlight a problem here, which if you're doing physics might not be super clear, is that definitions of higher categories become quite complicated for higher numbers of n. So for example, let's say you are interested in defects in a four-dimensional quantum field series, they should form a 4 category. And just looking at the definition of a 4 category, if you want to give all the pieces going in and all the coherences they need to satisfy, just the definition takes about 50 pages. And then if you go up to higher n, it just becomes hopeless. And so the problem here is really that the definitions are hard to have explicit control over. And I would say this is somehow how higher category theory was done in the last century, which was really trying to give all these coherences explicitly, and it has been extremely successful in low dimensions, like especially in dimension 2 and 3. These things can be done. There are a lot of hard and impressive work, but at least to me, it seems hopeless if I want to go to dimensions 4 or higher. And so in this century, people started to look at different approaches. I will not explain them in great detail, but the idea is to, instead of giving all the relations explicitly, is to package them into some ideas from homotopy theory. So there are some models which are homotopical or more topological in nature, and then, as at least to me was both pointed out independently by David Jordan and also Peter Teichner, that these models somehow already seem closer to what one would do in physics with topological defects anyway. So I just want to highlight that it seems like these modern models really are in some sense easier to implement in physically relevant settings. And I just want to give a sketch of one of these models for two categories, but you can imagine that this also extends for arbitrary n. I just somehow am a bit limited by my drawing abilities. There's this definition of what's called a twofold Siegel space. And this is a structure that's a model for a two category. And as a structure, it assigns to elements of some category delta op squared, which are labeled by two integers, 3 and 2 for this example here. It always assigns a space. And you should think of these numbers telling us how many planes we put. So the 3 says there are 3 surface defects, 3 line defects in 2D. And then the number 2 tells us that there are 2 point defects in each of them. These are these red dots. And then what a twofold Siegel space assigns to this picture is just a space or the collection of all ways of labeling this with objects, 1 and 2 morphisms. So a point, let me maybe do this in orange. A point in here would be something like collection A, B, C, then 1 morphisms F, G, H, and so on, and some 2 morphisms for all the red dots. And the labeling like this would be a point in the space. And then this whole space is the space of all these types of labels. Just erase this. And now,
sorry, can you explain what you mean by space? Is it a topological space or something?
Yeah, I mean topological space here.
And what is the benefit in having, I don't know, topology on the set of labels?
It allows you to say what it means to move them continuously, for example, things like that. And you could also think of it as a set. If you want to have a set, the axioms will look slightly differently. But it means something like the labels are allowed to themselves have internal structures. Or be a bit of a topological space. I think some things are easier to handle if they have buffer topology. I would prefer not to go into too many details, but yeah. Are there other questions?
Yeah, I have a question from much earlier. You will be talking about working with oriented theories and logically fixed points. Is that what you were alluding to?
Actually, here, these things are even there. What Ayala Francis call a very frame theory. Oriented theories still allow me to draw some less rigid diagrams, which you cannot see here. This would somehow be the same as an oriented thing, but I will comment on that a bit later. So this is somehow even more rigid than being oriented. Okay. Now what do I want to say here is that now if you have these configurations of labels, there are two types of operations you can do. The first thing is you just pick some subregion, like this one here, and you restrict your labelings to this region. So you expect that there's a map from the value on 3.2 to the value on 2.1, which is just restricting the labels to the smaller subregion. And the other thing you expect is that you can somehow collide defects or fuse them together. So you can move these two defects together and get a defect configuration looking like this, which would correspond to a map in this direction. And then a Siegel space somehow just takes the structure, these maps, and imposes some type of conditions on it. So one of them is some locality or sheaf-like condition, meaning that I can recover the value on this diagram from knowing the labels on all the smaller boxes, something like this, and how they intersect. And then there are some additional conditions which are related to identities, meaning that there are somewhat trivial defects, which I don't want to go into. But I mean, somehow if you would have never seen higher categories at all, just know about how topological defects fuse together, you might find the structure a natural structure to consider, and just want to point out that this is something which independently has appeared in mathematics. And now, sorry, what might be natural from a physics perspective is that our defects don't need to live on planes, right? We don't need to have our planes with some of our lines which sit nicely oriented in R2. I can have more general defect configuration. So for example, this would be a completely valid defect configuration to evaluate. And I can still do the same type of operation. So I can take a region and restrict to it, or maybe I take a larger region like this one and I collapse it to a point. And the idea of some ongoing work in progress with Claudia Scheinbauer and Pelle Steffens is to take this physical intuition, put it into some type of mathematics, and then use this to model higher categories with extra structures. In this case, the structure we expect to get is the notion of having adjoints. So the idea is really to start with this idea here, which relates Siegel spaces to configurations of planes, and extend this to more general defects. And what we try to do is we try to set up such a category, which we call Ln in general, and then we look at certain types of sheaves on that, which we expect to be related to categories.
So just to clarify this Siegel condition that appeared in the slide before, so that is only for configurations of defects which are somehow parallel to each other, like for filtering, but not symmetrical manifolds. Or...
Here it's only parallel. Things are only parallel. So somehow all these lines need to lie along one of the axes of R2, and then all these points somehow need to lie on the lines, yes. So there's no bending around in this thing.
Thanks.
Whereas over here, we would allow arbitrary types of configurations. Yeah, so this was mostly an aside on the open question how to rigorously construct these type of categories of defects. And this framework of somehow looking at these local pictures and figuring out what all possible labels are should be implementable in any model of quantum field theory you like. I should highlight that, again, somehow without really knowing that this is what's happening, is that in Claudia's model for higher Morita categories, she, roughly speaking, takes this picture and implements it in the Costello-Graham factorization algebra world when restricted to topological theories. So if you look at locally constant factorization algebras on these type of pictures, this would be just the defect configurations, and you just directly recover models for higher Morita categories. But it would be interesting to implement these type of things in like non-topological field theories. This was just a small aside on how to construct these categories. Now, what I want to focus on for the rest of my talk is what structures do these categories have? I mean, one structure there's adjoints, which roughly means if I have a morphism from A to B, then I can also bend it around or read it in the other direction to get a morphism from B to A, which satisfies these snake-like relations. And categorically, these type of things are called adjoints. Another structure which is present on these categories is that if I have two topological defects, F and G, I can take their superposition, which will result in a new topological defect. Yet another structure is that I can stack series on top of each other, and then I can stack defects in the two different series on top of each other, which induces some type of monoidal structure on these categories of topological defect. In general, point defects we are allowed to take linear combinations of point defects, meaning that the n morphisms in our category are always a complex vector space, meaning that the categories are linear. And then another thing we can do is we can, or physically one can do is one can take a bunch of defects, try to condense them to construct new defects, which on the mathematical side corresponds to these things being idempotent complete in a certain sense. But the main new idea I want to present in my talk is that in addition, these things should have some some type of higher dagger structure, which I will explain what it means, but it's related to the question of what type of diagrams we allow to draw and what additional structures corresponds to. And just as a small motivation is that if you look at oriented series, then what you have in addition to just having adjoints or two category are these things called quantum traces. So if I have a morphism, an endomorphism of some morphism F, which is this blue line here, going from a orange region to a pink region, then I can form from two traces of it, which are, one of them is a point operator in the orange region, the other one is a point operator in the pink region, by looking at this circle and then filling it in with the region. So this is just some type of trace. And in a general category with adjoint, there's just no way of defining such a trace, because if you would go around, instead of going back to the original morphism, you would end up with a double dual. And these things, this structure has already been observed in the work of Davidov and Grunkel, and they call this, or they noted that this is what people call a pivotal bicategory. So if you look at two-dimensional oriented series, there's really this additional structure present on the category of defects, which corresponds to these two notions of quantum traces. And the idea is to somehow try to have a more systematic framework, which tells you, if I pick a specific type of tangential structure, what additional structure do I get on the equals? Before talking about the general framework,
Sorry,
I just want to.
Question.
Sure.
What do you mean by point defects formally?
Just anything which is a point, like a topological point defect.
Okay, and that fits into the definitions from before, or?
Yes. I mean, I'm a bit agnostic about a specific model of quantum field theory. So you can implement this in different ways. Since in a topological theory, you have like some operator state correspondence. So you could always think of it as being in the state space on some sphere linking your point, or something like that. Whereas in other settings, it's a bit harder, but.
Thanks.
Here they should always be topological. I will, except on the last slide, never talk about non-topological defects. So if I say defect, you should always think topological. Oh, and if I say operator, I also mean defect. I somehow use these words more or less interchangeably. Oh. Okay. So I just wanted to somehow start with a simple motivating example, which is just what happens if we look at one-dimensional unoriented quantum field series. But as a warm-up, let's look at the oriented case. So defect configuration locally looks like something like this. I have some region A, some region B, some region C, and then I have some point defect F and G between them. And all of them are oriented. So I have these arrows which tell me a direction, and I just use these arrows to figure out from where to where F goes. So I'm saying, oh, F is a morphism from A to B, because that's the direction my manifold is oriented in. And G is a morphism from B to C, so I have this type of picture. And now, somehow this is just an abstract manifold or spacetime we want to evaluate our series on. It doesn't really matter how I draw it. So I could equally well have drawn this picture and then put my arrows going the other direction. It's just exactly the same picture. It's the same manifold. I have just drawn a different picture for it. So both of these pictures correspond to the same type of composition here. But now if I'm in an unoriented theory, the local picture I have looks like this. So I have some A, I have some B, and I have a point defect between them. But I don't have any orientation which tells me that I should read this left to right or right to left. So these two pictures, somehow it's hard for me to distinguish in which direction I read them. And what one does instead is just somehow allow, say, both ways of reading them are valid. So to turn this into a morphism, I just pick some random orientation on it, and then I read it as a morphism. But this means that the same morphism F I can think of as a map from A to B, which I call F here. Or equivalently, I can think of it as a map from B to A, which I call F dagger. And you see that these two things are somehow related by just flipping the direction in which I read the picture. So it means that if I take F and I take its dagger, and then I take its dagger again, which means I go from here to here, and then I go back, I just need to get F again as the morphism. So in addition, the category of defects in an unoriented theory has this additional involution on morphisms, which reverses the direction of composition. And now if I take this picture, what it tells me is that if I read it in this direction, I get, so if I read it in this direction or in that direction, or I flipped it so I can read it this way, it means that if I look at the dagger of a composition, so this would just be collide these two things and reverse the direction of reading it, then it's the same as taking dagger of G and composing it with dagger of F. So it reverses the direction of arrows, but also reverses the way in which we compose them, which is necessary for this to even compile. And from these pictures, we have somehow rediscovered what people usually call a dagger category, which has been introduced to find an axiomatic categorical framework for quantum mechanics, also been useful in other areas. So it's just as a definition, it's a category C, which is equipped with some functor, which is this dagger operation here, which goes from C to C op, which satisfies the condition that it's the identity in object. And if I apply it twice, it gives me back the identity. Yeah, and so somehow higher dagger categories are just a way of generalizing this to higher dimensions. Okay. So I just wanted to, I will now spend maybe 10 or 15 minutes, maybe a bit less, talking about what I mean by tangential structures on defects. The discussion might be a bit technical, I apologize for this, but I somehow don't know a good way of defining these things. Otherwise, I will try to illustrate many concepts by examples. And then later on, you can also somehow ignore most of it and just think of things being oriented and living in something oriented, or being unoriented and living in something unoriented. But the question this is related to is what type of defect configurations do we allow? For example, if I look at a theory defined in R3, am I considering defects which bound a line defect but are Möbius? So I have this Möbius strip here, which bounds a line defect, and I could ask, is this a valid defect configuration I should be allowed to evaluate my field theory on? Or maybe I have some surface defect in a 4-dimensional theory, which forms a Klein bottle. And then I asked, is this somehow something I would be allowed to put my defect on or not? And the fact, or the reason I've chosen these two defects is that they don't admit an orientation. So both of them are as manifolds unoriented. And you might ask, can I evaluate my field series on unoriented things? Or maybe oriented things. And just a good way of talking about these additional structures is this framework of tangential structures. So as I said, not being oriented is an example, being oriented is an example. Having a spin structure, which is relevant for fermions, is an example. Maybe having something like a pin plus or a pin minus structure would be an example. Another important example is the notion of a framing, which is the trivialization of the tangent bundle. And in general, these structures are encoded by specifying some space, which we might think of as a classifying space of some group Hn, which comes with a map to BON. And then any manifold has a tangent bundle classified by a map to BON, and a tangential structure is a lift of this to BHN. So it lifts the frame bundle of the tangent bundle to a bundle with HN structure in a way compatible with this map. Yeah. And then the example corresponding to orientation is the BSON mapping to BO, the example corresponding to B spin is the classifying space of spin mapping to the classifying space of BON. But so far, this is just tangential structures on one manifold at a time. And now, if I have a defect configuration, what this really is what's called a stratified manifold. Technically, I assume them always to be conically smooth. I won't go into any details here. But what this means is more than a manifold. So there's some manifold, but that has some embedded submanifolds or things which might not even be embedded, and they are allowed to meet at lower dimension manifold. So the regions of this type of picture, they are called strata. So there's two-dimensional strata here. Then this red circle would be a one-dimensional strata, and this point would be, or these 2 points here would be zero-dimensional strata. And this is roughly a stratified manifold. And now you could imagine situations where you want to equip this with tangential structures, but different stratas with different tangential structures. So for example, I might ask this the two-dimensional stratas to be oriented, but my defect or my one-dimensional stratas to be not oriented, which is exactly the situation we have here. Now 3 has a good orientation. I just pick one, and then I can look at an unoriented stratification, which comes from a Möbius strip. So these type of things. Maybe you want to have some fermions on your one-dimensional stratas, but no fermions on the two-dimensional stratas. So you equip this with a spin structure, something like that. And then you want all these different tangential structures to nicely fit together. And this is what the framework of tangential structures on stratified manifolds allows you to do. So what happens here is that if I'm at a stratum sigma here, which for simplicity I assume to be embedded, what happens is that I have a tangent bundle for it, but this also includes into the tangent bundle for the manifold M. So it also includes into the tangent bundle of this larger manifold M. And then this has more information than just the tangent bundle. I also have the information of the normal bundle to sigma. So it comes with a map to BO1 times BO1 here, which specifies both the tangent and the normal bundle. And now, roughly speaking, before we've seen that the tangent bundle for an ordinary manifold is a map to this classifying space BON, whereas for a stratified manifold, I should say that this is roughly speaking a moduli space of n-dimensional vector spaces. So to every point, I somehow just assign the vector space its tangent bundle is. But now if I have a stratification, somehow what can happen is if I on a stratum and I leave it, then the dimension jumps. So it's not a continuous family of n-dimensional vector spaces over the stratification, but there's some jumping. And for this, one can look at this category of vector spaces and injections, which is equipped with its usual topology, which roughly speaking also allows things to jump by inclusion. So these type of inclusions show up. And then what Ayala, Fuentes, Rosenblum show is that in these settings, the tangent bundle of such a stratified manifold is a map from its exit category to this category of vector space and injection. The exit category is just the category where the objects are points on the strata, and then morphisms are paths in the manifold which are allowed to leave strata but not enter strata again. And so to every such point, it would just assign the tangent space. And then if I leave a stratum, it would use these embeddings to construct the value on that. As I said, this is probably a bit technical. I will go through some examples later. I just want to highlight this as a good framework of discussing this stuff. And now, using this definition, we can take the previous definition of a tangential structure and just extend it to stratified manifolds by saying that we need to specify living something over this vector spaces and injections. And then a tangential structure is just a lift of the tangent bundle to this larger structure. Okay, so this is the abstract formulation. Let's look at some examples. The easiest example, or the most fundamental example, is the notion of a Berry framing, where the structure living over vector spaces and injections are just the natural numbers, 1, 0, 1, 2, and so on. with a morphism from 0 to 1, a morphism from 1 to 2, and so on. And I map this to vector spaces and injections by mapping the number n, for example, 2 to R2, and these maps to the inclusions as the first coordinate. So this would be inclusion as the first coordinate. This map would include R2 into R3 as the first two coordinates, and so on. And then what is the corresponding tangential structure? What it consists of is it's this framing of the tangent bundle. So it's an isomorphism from the tangent bundle to a trivial rank K bundle if sigma is a K-dimensional stratum. It also trivializes the normal bundle. So it's a map from the normal bundle of sigma to Rn minus K if the ambient manifold is n-dimensional. And then in addition, now if I look at the tangent bundle of M restricted to sigma, this is always the sum of the tangent bundle of sigma plus the normal bundle of sigma, which I can now trivialize using these two framings. But I also want the manifold M to be independently framed. So I have another framing here. And then I want to relate these, continuously deform these two things into each other via homotopy. So there's an example here of a vary framing. I take this line living in R2. I frame my R2 just as using the blackboard framing. And now I tangentially frame my line like this, and normally frame my line like this. And then this pink information just tells me how to rotate this picture into the normal frame, into this framing. And I could have chosen to also rotate in the other direction to get back. I could also have chosen to somehow do like a few 360 degree rotations on top of it. So this H really encodes additional information. And in this case, there's exactly an integer verse of them, which encodes how often one. So now, as I said before, there are these things called, I was using these things called quantum traces. If I'm in a vary frame setting, I cannot form them because a circle living in R2 doesn't have a vary framing. So I have an ambient framing. I have my tangential framing here. This has also a normal framing. But what I cannot do is continuously deform these framings into this one. Should probably have drawn something here. So I have this picture. And now you might think that the pink thing could just rotate things like this. But then if I start over here and go once around, the thing I started with does no rotation. The thing I end with will do a 360 degree rotation. So this is not continuous along this pattern. So in particular, in this vary framed world, I cannot draw circuits of this type. So I cannot consider quantum dimensions for vary framed defects. Whereas here, I just wanted to highlight what happens is if I have an arrow going down, then its normal framing needs to be like this to be compatible with the ambient framing. But I have two choices on how I rotated it back, which are different vary framings. And mathematically, they correspond to the distinction between left and right adjoint. Just want to mention another example of tangential structures on defect, which is well discussed in this paper on topological symmetries by Friedman and Telemann, and then the relation to the formulation I've mentioned before has been explained in this paper here. So I just look at the simple situation where I have one defect of dimension k living in some space-time of dimension m. As I mentioned before, sigma has a normal and a tangential bundle, and then to specify this tangential structure, I need to have some space living over this product, and then it needs to be compatible with BOK and BON. The map in this direction is just the direct sum. Here I just need to specify some map, and then roughly speaking, the tangential structure corresponding to that is on sigma I have some xk structure, on TM I have some X on TM I have some XN structure. I can look at the normal bundle to sigma plus the tangent bundle. This comes with a map to this space, which I need to equip with an xk plus n structure. And then all these structures need to be compatible by some type of doing. Yeah. But as I said, a good example is just think of every stratum independently being oriented. That would be a good example of a tangential structure as well.
Could you maybe tell a couple of words on how this could be used to describe how Wilson lines and Chern-Simons are framed, because they are not framed, they are framed in 3D somehow, very similar.
Yes, so right, what happens in 3D, imagine you asked, I have some 3D thing, and I want to equip this with a vary framing, right? What is this? This is a tangential framing. So this is just, again, something going in this direction. But then in addition, now I need to see if I can draw that there's some. So I have my normal bundle, which I also need to frame. And I need to frame it in such a way that it's compatible with some ambient thing. So I need to give some normal framing, which could be something like this, right? But now you can already imagine that if I follow the line, my normal framing can wind around the line. So this is why in Chern-Simon theory, your line observables often depend on either ribbon structure, so a bit of a thickening of this line, which would give you this normal direction or framing. I should also mention if you have one of these vectors, the other one is somehow fixed. So you can also just pick one of the vectors and this can then wind around. Is that what you wanted to know?
Yes, but the ambient manifold there need not be framed. It's enough to be oriented, so you don't have this condition that you can deform somehow these three arrows on.
I mean, you can also put SON here. In this case, the condition is you have these three arrows. These three arrows will give you an orientation, right? And the orientation needs to agree with the orientation of the ambient manifold.
I see.
So, which all again means somehow if I fix this direction for the normal framing, I'm only allowed to choose this one. Because if I would choose this one, it would not be compatible with the orientation. So in this case, somehow the lines would be vary framed, but the ambient manifold would be oriented. And this is a valid structure which fits into this framework.
That's very nice.
And you can do more fancy things, right? You can put spin structures on things, or maybe you put pin structures on something which is compatible with spin structures on other things. And it's just a good framework to handle all these cases at once. Okay.
Sorry, the maps, Lukas?
Yep.
Are these maps strict lifts or are these only up to
homotopy? Up to homotopy. Everything always up to homotopy. Yeah. I mean, somehow you can, if you want, pick a vibration here, and then you put model them in terms of strict lifts. But like the framework is somehow set up so that these things are up to homotopy. And now the question I want to come back to is like, how do these things form a categorical structure? And the answer is just they don't. Like if I pick an arbitrary tangential structure in this general framework, there it's quite hopeless. And an example to see is like take a disjoint unions over BONs for all n's, and I include this into vector space interjections. Then a manifold with this stratified manifold with this tangential structure is just a disjoint union of manifolds of arbitrary dimension. But if I take a defect, something like this, there's really no way of talking of the source or target because it's not embedded into anything. So in this way, there's just no hope for source and target. So the framework is too general to allow for categorical structures. And the way of solving this is that we can come back to these vary frames, but they somehow always give us instructions what is a source and a target of a morphism. So in the vary frame setting, I somehow for every morphism, I know in which direction it's going, and I know what its source and target is. So these vary framings are somehow the most rigid structure where I can talk about about a categorical structure. And now I define a pointed tangential structure to just be a tangential structure which receives a map of very framing manifold. So for any very framed manifold, I can construct a structure, a manifold with this type of structure. Okay. And now in this setting, if it's pointed, I can always read of some category of topological defects of this tangential structure. And now there are some examples where some additional structures are known. So as I already mentioned, if I look at oriented two-dimensional series, get a pivotal bicategory. For oriented three-dimensional series, we get a gray category with duals. The expectation is that if I put very framings here, I don't get any additional structures. The only thing I get is the existence of adjoints. The argument I've presented before shows that if I look at O1, I get just an ordinary dagger category. And the proposal I want to advocate for in this talk is that in general, this category is a higher version of the notion of a dagger category, which depends on this tangential structure Bn in such a way that it recovers these examples. We just have this one slide saying a bit about what are higher dagger, or like somehow how we started thinking about these notions of higher dagger category. And our motivation really didn't come from topological defects. So it's a bit of a surprise that they can be applied in the setting. What we really try to understand is how to formulate unitarity in the setting of topological field series, where if you are not extended, you can say there are certain dagger functors, but then if you want to include locality, you need to extend this to fully extended field series, so you need to work with higher categories. And the other input motivation for us was this notion of what one might call higher functional analysis or categorified functional analysis. So notions of higher Hilbert spaces, of C-star categories and C-star algebras. And starting from these two motivations, we spent some time working out a proposed setting of this notion of higher dagger category. And then later on, somehow it turned out that they seem to match the structure people have discovered for topological defects. And what I want to do in maybe the last 10 minutes of my talk is somehow try to explain this direction. So I will not talk about these other motivations which really were behind the definitions, but I just start with categories of topological defects and try to sketch part of the structure of the higher dagger category. You can read off of that. Okay. So the question is, what is this extra structure? And let me start with what happens if I look at these very framed things. Then I can, or in general, if I have my defect configuration, my configurations are somehow always local configurations living in some Rn, and I can act with the orthogonal group on them. So for example, I can take this configuration and reflect it to something looking like this. And this means that the orthogonal group should always act on these categories of defects, at least in the very framed setting. So there's an action of On on this category, there's some action of On on these diagrams. And this led us to expect the following conjecture is that if I look at the automorphisms of all categories with adjoints, then this contains On. And the action of On is somehow in the diagrammatic interpretation by acting on these defect configurations. And then some other arguments led us to believe that the full automorphism group is the piecewise linear group instead. And for n equals 1, this is well known. For n equals 2, there I have some joint work with Luke Stiehauer where we prove this. Yeah, but then for higher n, this is widely open and might be hard to prove in general. As I said, the reflection, so for example, reflection along this line would send a picture like this to a picture like this. And what it does to a category C, it sends it to the category C, which reverses the directions of isomorphism. But this is somehow the action we get in a very framed theory. Now, if my theory only depends on an HN structure, some of these actions will not do anything to this category. And exactly the part of Hn will be trivialized. So in addition, these categories will have some type of fixed point structures. So these things which led us to define this notion of what we call an Hn volutive n category as a fixed point for the induced Hn action on categories with adjoint. So for example, an O1 volutive category is a category which comes with an anti-involution, so an equivalence from C to C op, which squares to the identity. And you should think of this as reversing the orientation of your topological defect. So it's like D of F going from some orientation reversal of A to some orientation reversal of B. And the SO2 version of it corresponds to an identification between left and right adjoint. Let me not explain this in detail because I will try to finish on time, but if you want to see more details, feel free to ask me later. What happens now, I mean, already here, you see if I'm in an unoriented theory, this orientation reversal of my theory should really just be the same theory again. So the space of Bn theories sits in this larger category. It's the space of objects, but it has this additional structure of a fixed point for this Hn structure. So what happens in the setting of one-dimensional topological field series is that the category here is just finite dimensional vector spaces. The involution is taking the dual, but then unoriented series come with a self-dual symmetric pairing, which is a map from V to V dual, which satisfies some conditions. And meaning it factors through these fixed points. So the spaces of field series, they in addition have some fixed point structure for this evolution. And this happens in general if I look at the category of codimension I defects, they are invariant under doing some n-I rotation. And this picture of having these different categories all sitting into each other, which have fixed point structures for various evolutions, and then compatibility is what we used to, or which we suggested to be the definition of a higher dagger category. Just some examples. If I look at O1, there's a theorem that this structure here corresponds to ordinary dagger categories in the way I've introduced them. The SO2 case corresponds to pivotal bicategories, which is a theorem from this year. Okay. And then I just want to mention at least one theorem I've proven is that if you assume the stratified cobordism hypothesis, then you can build these higher dagger structures in cases where tangential structures are stable and have the direct sum. So I somehow verified this in a dimension-independent way for the class of tangential structures. Okay. Let me try to highlight one of the benefits of this framework, or why should you care that this additional structure is present on categories of defects. It's that in a dagger category, you have different notions of equivalence. So if I'm in an ordinary dagger category, I can ask for what's called a unitary isomorphism. So an isomorphism where its dagger is equal to its inverse. And in general, objects might be isomorphic, but not unitarily isomorphic. And these would be exactly the morphisms in the space C0. Or similarly, in a pivotal bicategory, I might ask for what's called a pivotal equivalence, where I ask F inverse to be the same as the dual of F, which in this case, in a pivotal bicategory, is both the right and left dual. And you might assume that this always holds if you have seen some category theory. But I want this somehow be true for the right and the left dual at the same time, which implies that I need these two quantum dimensions to be trivial. These are the morphisms in C0 again. And if I look at this at oriented two-dimensional field series, what I find is that I get pivotal symmetric data separable Frobenius algebras here, separable algebras, and then separable algebras again, and bimodules between them. The important thing is that pivotal equivalences are what corresponds to the most naive notion of symmetry, which are just natural isomorphisms of the functors of the DQFTs. However, these pivotal equivalences are stronger than just asking the topological defect to be invertible. So there's this additional condition on the quantum dimension. And this happens more general is that probably you've heard the slogan that symmetries equal invertible topological defects. And at least for topological series, this is not true as soon as you're in a setting where you are not very framed. But what's always true is that symmetries equal the dagger notion of invertibility. So if you have the stronger notion of invertibility, which here was unitarity or pivotality over here, then they are exactly what corresponds to symmetries in the setting. So if you care about the relation to symmetries, this dagger structure can be quite important, I would say. Now let me just open with some, let me conclude with some open questions and some outlook. So I think for every notion of a higher dagger category, there should be a corresponding notion of doing a condensation. So if you condense defects, you want to preserve the type of tangential structure you have. And in the orbifold construction, this is done for oriented series. The condensation of Gayotto-Johnson-Veit does this for very framed series. But in general, it's not so clear what structure I exactly need to keep to preserve pin structure or something like that. And there should just be a general framework which uses this theory of higher dagger categories. And already orbifold construction strongly use pivotal structures. Then most examples of these structures are not really known. So we expect that the SO3 version matches the notion of gray categories with duals. So many details are unclear. We give a list or a description of these O2 dagger categories in joint work with Luke Stiehauer. Niels and Tim, they discussed the spin R and the spin version, but what is the spin 3 dagger category? I don't have a good description. And then another probably also interesting outlook is to now take these dagger structures for topological defects and start with notions of unitarity. So look at what structure we get in unitary field series. And then I just want to mention one open question, which is not related to my talk, but I am extremely interested in learning more about is what survives of these categorical structures if I also have some non-topological directions. So an example of these would be fractons, which are topological in some direction, but non-topological in other directions, or in the setting of twists, these holomorphic topological twists of supersymmetric series. Often they are topological in some directions and then holomorphic in others, which leads to some interesting interplay between categorical structure and between holomorphic structures and categorical structures. So I just wanted to highlight this as an interesting open question. So with that, let me thank you for your attention.
Are there some more questions for Lukas?
I have a question.
Yeah, go ahead.
So you mentioned that you're not declaring any model for n categories, right?
Yes, I'm not using any specific model for n categories here.
But you had the result that your higher dagger categories have adjoints. It's very similar to what Ayla Francis did for their factorization homology program. They also didn't declare any infinity comma n category model as far as I remember, but do you know what's the relationship between this and this cellular realization of this Joyal n category by any chance?
You mean this specific setting here? So
this one looks much like striation sheaves.
Yes, it's in some sense Poincaré dual. There are some subtle differences with the type of tangential structures we allow. Here, these things are very framed, where morphisms are not necessarily very framed. Also, we allow these type of collapse maps, which in a striation sheaf you don't have because you just have embeddings for stratified manifolds. So it's similar to this Ayala Francis Rosenblum work, which relates ordinary categories to sheaves on certain stratified manifolds. They ran into some problems with their work, leading to the fact that their main results doesn't hold for n larger than 3. There's still the belief that this works in the in the stably framed setting for things with adjoints. I think our framework is a bit less ambitious than theirs. We somehow only allow diagrams which live in some R2, or in the setting R2 or some Rn, and our inspiration came more from the physics, where there, so I think, comes more from the topology. Roughly speaking, they should be related by some type of Poincare duality, but making this precise is quite hard.
At least in R2, you mean, right?
What?
At least for R2, can you make this precise, do you think?
Sorry, I couldn't hear the last part of the question.
At least for dimensions less than 2, can you make this precise, this equivalence?
Not really, because they still, but what they prove in dimension less than 2 is that they have, like, I forgot how they call it, but they have these sheaves on very frame stratification, 2-dimensional stratified manifolds, and they show that these things are ordinary 2 categories. Whereas we have these sheaves on certain stratifications of R2, which corresponds to 2 categories with adjoints. So already our results are slightly different. And they plan to prove a result involving stable framing, which allows you to include, or which includes adjoints. However, that has not appeared in the literature. So it's a bit hard of comparing these things. I mean, you can somehow draw Poincare dual pictures and they will look like the pictures they've been drawing, but I don't have a precise statement about the relation.
Okay. Any more questions? If not, before we thank Lukas, afterwards there will be a reception which will be set up in roughly half an hour. So please stay around for this, and before that you can already take a look at the posters, discuss all the open problems we heard today, and other open problems you might have brought yourself. So now let's thank Lukas and also all the other speakers of today.